Hello, and welcome to this online lecture. My name is Patty Kokish, and I teach both in-person and online classes at Ivy Tech in the Northwest region. In Chapter 5 of Math 200, you learned all about probability. You learned about classical probability, which relies on counting techniques to obtain theoretical probabilities. Probability models listed all of the possible outcomes in a probability experiment. In Chapter 6, we will be looking at the probability models for random variables. We will first talk about what a random variable is, and then we're going to describe their distributions. Once we've done that, we're going to take a look at one discrete probability distribution in particular, the binomial distribution. So let's start with Chapter 6. Section 6.1 is about discrete random variables. The objectives in this section include distinguishing between discrete and continuous random variables, identifying discrete probability distributions, constructing probability histograms, computing and interpreting the mean of a discrete random variable, interpreting the mean of a discrete random variable as an expected value, and then also computing the standard deviation for a discrete random variable. So let's start with the first objective. This is distinguishing between discrete and continuous random variables. So a random variable is a numerical measure of the outcome from a probability experiment. So its value is determined by chance. Random variables are denoted using letters such as x. So let's talk about an example. Let's say that we flip a coin 2 times. If you flip a coin 2 different times, the outcomes of the experiments are going to either be that you get heads and then heads, heads and tails, tails and then heads, or tails and tails. So rather than being interested in a particular outcome, like getting 2 heads or 2 tails, we might be interested in the number of heads that we obtain when we flip the 2 coins. Since the outcome is numeric, meaning we could either get 0, 1, or 2 heads, the outcome is called a random variable. So let's talk about discrete random variables first. Discrete random variables are countable, essentially. The values of a discrete random variable can be plotted on a number line with a space between each point. So they take on values of maybe 0, 1, 2, 3, 4, and so on. Continuous random variables are different. They have infinitely many values. So the values of a continuous random variable can be plotted on a line in an uninterrupted fashion. So you could have values like 1/2, 1/16, 1/100th, anything between 0 and 1. So it's not necessarily countable. So let's look at a couple of examples where we distinguish between discrete and continuous random variables. Also, when possible, we want to state any of the possible values for the random variable. So let's say that we're talking about the number of light bulbs that burn out in a room of 10 light bulbs in the next year. So we have a room that has 10 light bulbs in it, and what we want to count is the number of light bulbs that burn out in a particular room. So if we're talking about that, we could have 0 light bulbs that burn out, 1, 2, 3, all the way up to 10. So this is countable, which means that it's discrete. And x can be values from 0 all the way up to 10. Because you can't have like half of a light bulb burn out, that wouldn't make any sense. But you can have 0 light bulbs, 1, 2, all the way up to 10. The number of leaves on a randomly selected oak tree. This, again, is countable. If you think about it, well, I don't really know what the upper bound is going to be for this one, but you could have no leaves on an oak tree. You could have 1,000 leaves on an oak tree, but you can count the leaves, okay? So you can imagine yourself maybe counting them. You wouldn't necessarily count half of a leaf, okay? You would just be counting the whole leaf. So that is also discrete, and x is 0, 1, 2, and then you just see ellipses there because there isn't really an upper bound. Now, if we're talking about the length of time between calls to 911, this one is actually going to be continuous with your time greater than 0. So you can't have a negative time. But if you're thinking about length of time, it could be a minute or 2 minutes, but maybe it's a minute and a half, or maybe it's 36 seconds or 76 seconds. So you can't necessarily count all of those times. So that one is going to be continuous. So discrete is countable and continuous is not. So continuous includes an entire shaded number line, whereas discrete is just particular points on the number line. All right, for objective 2, what we want to do is actually identify discrete probability distributions. So first, let's talk about what a probability distribution is. A probability distribution essentially just provides the possible values of the random variable x and their corresponding probabilities. So it can either be in the form of a table, a graph, a formula, and so on. So let's look at this one that we have here. The table to the right shows the probability distribution for the random variable x, and x in this case represents the number of movies that are streamed on Netflix each month. So if you look, we have 0 to 5. We can't have half of a movie, okay? That would just be considered one whole movie. So we have values of 0, 1, 2, 3, 4, and 5 for the number of movies streamed. And then we have different probabilities associated with each of those. So we have about a 6% chance, or 0.06 for 0 movies, a 58% chance, or 0.58 for 1 movie, and so on. So there are a couple of rules that have to be true in order to have a probability distribution. The first rule is that when you add up all of the probabilities, that has to equal 1. So what you see by number 1 there, that's a summation symbol, okay? So what that means is that the sum of all of the probabilities of your x's is going to be equal to 1. So if you add up all the probabilities, you should always get 1. The other thing that needs to be true is that each of the individual probabilities has to be between 0 and 1. It could be 0, it could be 1, but it can't be a negative number and it can't be larger than 1. So those are the two basic rules that have to be true for a discrete probability distribution. So the next thing we want to do is look at some examples of things that look like probability distributions and determine if they actually are probability distributions. So again, we need to check those same two things. We need to make sure that all of the probabilities add up to 1, and then we also need to make sure that all of the individual probabilities are between 0 and 1. So if we look at this one, all of our probabilities are between 0 and 1, so that's good. But if you go ahead and take a calculator and add up the 0.16, 0.18, 0.22, 0.10, 0.3, and 0.01, you actually get 0.97. So this one is not going to be a probability distribution because the sum is not equal to 1. So you have to keep in mind the sum always has to equal 1. All right, let's look at another. This one is very similar to the last one, but they changed. At x equals 5, we have a probability of negative 0.01. Now, if you guys remember that second rule that we talked about, probabilities can never be negative. Probabilities always have to be between 0 and 1. So we cannot have a negative probability. So this one is not a probability distribution either. Let's look at one more. This one, again, is very similar. This looks good. All of our probabilities are between 0 and 1. And then if you actually add up the probabilities for this one, so if you add the 0.16, 0.18, 0.22, 0.10, 0.3, and 0.04, that one sums to 1. So this one is good. This is a probability distribution. All right, objective 3 is to actually construct a probability histogram. We looked at histograms when we talked about visualizing data back in a previous chapter, and this is pretty much the same thing, except a probability histogram is just a histogram where the horizontal axis corresponds to all the values of your random variable, and then the vertical axis represents probabilities. That's why it's called a probability histogram. So let's look at an example. We have that same one that we did before where you have Netflix movies that are streamed each month. And if we want a histogram, all we do is we put the number of movies streamed across our x-axis, and it's 0 through 5, 0, 1, 2, 3, 4, 5. And then we would put our probabilities along our y-axis. And what you'll see is that all of our bars are connected. That's what makes it a histogram. Difference between a histogram and a bar chart is that in a histogram, your bars actually touch. So this is a very good example of a probability histogram. All right, objective 4 is to compute and interpret the mean of a discrete random variable. So we have a formula here. It looks a little confusing, but don't be too afraid of it yet. The mean of a discrete random variable is just given by the following formula. Now, if you see that symbol there, that's a mu, okay? It's a Greek letter. So we say mu of x is equal to, and then again, that's that summation symbol. So it's the sum of all of the x's times their probabilities. So x is just the value of the random variable. P of x is the probability. So essentially, all you have to do is just multiply the random variable by its probability and then add everything up, and that gives you your mean. So we're going to look at an example in a second. All right, so we have again our, I think we have the same data, but for some reason it's presented with a different story. So this one tells us that we're renting DVDs from a video store in a single visit. So we could go in and maybe not find the DVD that we want, and we rent nothing. That happens about 6% of the time. We might just rent one movie. That happens 58% of the time, and so on. Maybe we rent 5. We watch a lot of movies, and that happens about 1% of the time. And what we want to find is the mean of this variable. So in order to do that, what you can do is just use that formula that we presented on the last side. Mu of x, or your mean, is equal to the sum of all of the x's times their probabilities. So it's not shown on this slide, but my suggestion to you is maybe create a column like right over here to the right of your bar chart, where it's x times p of x. So what you would do all the way down is you'd have 0 times 0.06, you'd have 1 times 0.58, 2 times 0.22, and so on all the way down. And that's essentially just what they're doing right in this line right here. Once you have all those values, you go ahead and you add them up, okay? You have to follow order of operations, make sure you multiply first and then add. And if you do that, you get 1.49. Okay, and you always want to make sure once you've calculated a mean that your answer makes some kind of sense. So if you think about it, what we're talking about is the number of DVDs that a person rents from a video store. It seems pretty reasonable that it's between 1 and 2 movies, okay? If we had gotten a mean of maybe like 10 or something like that, you should think to yourself, maybe that doesn't make a whole lot of sense that the average number of DVDs rented is 10, okay? So that's kind of what this is getting at. So we do have a couple ways of interpreting these. Now, the mean of a discrete random variable can just be thought of as basically what would happen if we repeated an experiment a bunch of times. So I'm going to walk through this definition here, but let's suppose that an experiment is repeated n independent times, and the value of the random variable x is recorded. So as the number of repetitions of the experiment actually increases, the mean of the n trials is going to approach your actual mu of x, the mean of the random variable. So in other words, we're going to let x1 be the first trial, okay? X2 is going to be the second trial, second experiment, and so on, up into n. So we have xn. So if you look here, you see that x bar, okay, that's how we read that, x with a bar on the top, is just equal to all of our experiments added up, so x1, x2, x3, all the way up to xn, and then you divide by n. That's just simply your average formula, which you guys already learned in a previous chapter. So you add everything up, and then you divide by the number of numbers. So what you'll find is that the difference between your x bar and your mu of x gets closer and closer to 0 as your n increases. So if you look at this, let's just say that this is actual data represented, I don't know, someone stood outside of a movie rental place and counted the number of DVDs that people rented for 100 randomly selected customers, and then they recorded that, okay? So you have a lot of people that rented one movie, some that didn't rent any, some that rented 2, 3. I think we have a 4 and a 5 on here as well. So what you want to do is compute the mean of this. So in order to do that, what you would do is you'd add up all of these numbers in this whole table, and then you divide by 100 because that's how many trials you have. And they did this for us. It would take us a little while to add all those up. But if you actually do that, you get 1.49, which hopefully you recognize that number. That's actually the same number that we expected to get, 1.49. Now, the idea is that we had a lot of trials. If you look back here, we had 100 trials. If we had maybe only 10 people that we randomly selected, or 5, we probably wouldn't have ended up with exactly 1.49. But the idea is that as you take a larger and larger sample, your x bar gets closer and closer to the mean of your random variable that you would expect to be getting. And what you see is exactly this here in this table, or in this nice little graph they show us. They have the trials along the bottom, okay, all the way from 0 trials to 100, and then they have the mean up here. This bar right here is the actual mean that we want. That's our 1.49. And what you notice is that over time, our mean kind of shifts, but it starts to get closer and closer to that 1.49. And then once we get to 100 trials, it's pretty much right on top of the 1.49. So when we only had 50 trials, we didn't have as accurate of a number for our mean, but once we did more trials, like up to 100, like I was saying, we get closer and closer to that mean that we were hoping for. All right, objective 5 is to compute and interpret the mean of a discrete random variable as an expected value. So because the mean of a random variable represents what we would expect to happen in the long run, it's also called an expected value. Now, expected value is typically denoted as E of x, and that's our expected value for our random variable. So let's go through, this is kind of a typical problem with life insurance. So let's say we have this term life insurance policy. It's going to pay a beneficiary a certain amount of money upon the death of the policyholder. So you typically have to pay some kind of premium for the policy, and that needs to be paid annually. So we're going to talk about one particular case, which is a life insurance company that sells a $250,000 life insurance policy that's good for 1 year, and they sell it to a 49-year-old female, and it costs her $530. So if you think about that, basically this 49-year-old female is going to pay $530 to the life insurance company. And if for some reason she does not survive the year, then her beneficiary is going to get a sum of $250,000. But if she does survive, then she paid $530 for no real benefit. And according to the statistics report, the probability that a female will survive the year at age 49 is 0.99791. So over a 99% chance that she is going to survive that year. So what we want to do is compute the expected value of the policy to the insurance company. So if you think about insurance companies, their entire goal is to make money. So we would expect that they're probably making money off of this policy, okay? So let's see how this works. So we list our two kind of things that can happen. Those are our X's. Either the person survives or does not survive. If the person survives, then the insurance company pocketed $530. So that's where this $530 came from. Now, if the person does not survive, then the insurance company actually has to pay out. So they made $530, but they ended up paying out $250,000. So if you subtract those two numbers, you end up with a negative $249,470. So the insurance company, if this 49-year-old female does not survive the year, loses $249,470. So the probabilities of these, which you also have to figure out, they told us up here, the probability of her surviving is 0.99791. So that's this probability right here. This is the one that we have to figure out. And you have to remember something about probability distributions from before in order to do this. And the important thing that you need to remember is that when you add up probabilities, they should always sum to 1, okay? So we know that 0.99791 plus something is going to give us 1. That's what we need our total to be. So in order to find out this something that we're not sure about, what we're going to do is we're going to take 1 minus this value right here. And if you actually do that, that gives you 0.00209. So that's your probability. And then expected value, we already talked about expected value, is just the same as your mean. So all you're going to do for this type of problem is, if you remember the formula for mean, all you have to do is take x times the probability, take x times the probability, and then you add those two things together. So that's exactly what they've done down here. And if you actually calculate this, you have to multiply first and then add, or in this case, you're subtracting. You're going to get $7.50. Okay, so that means that really for every 49-year-old female who participates in this policy, they're making on average about $7.50, okay? So they're not going to make money on everyone. They're not going to lose money on everyone. But in the course of all of these females who are purchasing this policy, that's on average what is going to happen, okay? All right, the last thing we're going to do in this section is to compute the standard deviation of a discrete random variable. This is objective 6. So the standard deviation of a discrete random variable is given by, and then you see these two formulas here that both look kind of gross, but they're not too bad if you pick them apart. Now, you can use either of these two formulas in order to do this. It really doesn't matter which one you use. So I'm just going to go through the pieces of them, and then as you're doing your homework, you can kind of decide which one you like more. So for this first one, what you do is you take your x's, okay, so you take all of the random variables that you have, you subtract the mean, okay, from each one, and then you're going to square that. Once you have those squared, then you multiply by the probability, and then once you have those numbers, you add them all up, and then take square root of that entire thing, okay? So that's one way to do it. The second way down here, what you do is you take your random variable x and you square it, then you multiply by your probability, okay? And then you add all of that up, and then you subtract your mean squared, okay? So they all use the same pieces. They all use x, p of x, and mu of x, but it's just a different order, okay? So these are two equivalent equations. You can pick the one that you like more. I want to point out again, x is the value of the random variable, mu of x is the mean, and p of x is the probability, okay? So let's look at an example. Let's do the same one with the DVDs. Now we already figured out that the mean was 1.49, and then these were the values that we had. We had 0 with a probability of 0.06 and so on. So the easiest way to do these types of problems is to go ahead and set up a nice table, and this is already done on this slide. So what you'll see here is that we have our x, we have our mean, which we already calculated, okay? You can look back at the previous slides if you've forgotten how to do that, but that's our mean that we already calculated. And then what we do, we're going to be using if we go back, we're going to be using this first equation, okay? So if we go back to this, first thing we're going to do is we're going to take our value, our x, and we're going to subtract our mean, our mu of x, and we're going to do that all the way down. So we do 0 minus 1.49, we get negative 1.49. 1 minus 1.49, we get negative 0.49, and so on all the way down, okay? And then what we do is we take all of the numbers that we have in this column, and we're going to square all of those numbers. So I'm going to do negative 1.49 squared. And keep in mind, whenever you square a number, it should always be positive, okay? So you should always end up with positive numbers in this column here. So if we take a look, we have all positive numbers here, all right? These p of x's, that's what was given on that last slide. That's already given, so you don't have to figure that out. So it's this 0.06, that's this right here. And then what we do is we take our, let's see, this is our fourth column, and we multiply by our fifth column in order to get this right here. And once you have all those values, then you add them all up. This gives you something called your variance. And then if you want your standard deviation, what you have to do is take the square root, okay? So for this one, we had a mean of 1.49 and a standard deviation of 0.9372. One thing I want to talk about before we start on this next section is that there are several ways to do this. If you are using a graphing calculator for your class, then there are instructions in the online textbook that show you how to actually get mean and standard deviation for a discrete random variable. So I would take a look at that if you are using a graphing calculator, then it does have that functionality so that you don't have to create this kind of nasty looking chart here. It's still important to understand the math behind it. But your graphing calculator will do that for you. All right, so let's move on to section 6.2. This is the binomial probability distribution. So again, we have several objectives in this section. The first objective that we're going to tackle is to determine whether a probability experiment is a binomial experiment. So a binomial experiment is a type of probability experiment, so we have to first determine if it actually fits that mold. Then we're going to learn how to compute probabilities. We're going to learn a couple of different ways to do that. We're going to also figure out how to compute the mean and the standard deviation for a binomial random variable, and construct some probability histograms for those. So first thing we want to talk about is what is a binomial probability experiment. So a couple of things have to be true. An experiment is said to be binomial if the experiment is performed a fixed number of times, okay, so it has to be a fixed number of trials. We call each experiment or each repetition of the experiment is called a trial, okay? The second thing that has to be true is that the trials have to be independent. So the outcome of one trial cannot affect the outcome of another trial. In addition to that, each trial has to have two mutually exclusive or disjoint outcomes. And I think you learned that in the probability chapter. So there are two outcomes. One is considered a success and one is considered a failure. And then the fourth thing that has to happen is that the probability of success is fixed for each of the trials. So let's look at a couple of examples. Oh, first we have to do notation, and then we're going to look at a couple of examples to determine if something is a binomial experiment. So notation that you're going to see used is that there are n independent trials, okay, so n is your number of trials. P is going to denote the probability of success, okay, and then we know from the previous section that 1 minus P has to be failure because together they have to equal 1. Successes and failures have to equal 1 because those are your two outcomes. X is going to be the binomial random variable that denotes the number of successes in the n independent trials. So X is the number of successes, n is the number of trials. So X has to be somewhere between 0 and n. All right, so first thing we're going to do is talk through kind of a couple different scenarios and determine which of the following are binomial experiments. So let's look at this one. A player rolls a pair of fair die 10 times, and the number X of sevens is recorded. So what that means is if you roll a pair of die, you could get a 1 and a 6. That would give you 7. You could get a 2 and a 5. That would also give you 7, or a 3 and a 4. But if you roll any other combinations, that's not going to give you 7. So what we're doing is we're counting the number of times we get a 7. So we want to know if it's a binomial experiment. So let's flip back for 1 second to this slide right here that talks about binomial experiments. First thing that needs to have happen is that each repetition is a trial, okay? It's a fixed number of times. Now the one we were talking about was 10 times, so that's good. Trials are independent, so that means that the outcomes of one trial will not affect another. So if you think about rolling dice, it doesn't matter what you get the first time, that has no effect on the second roll. So that's good as well. We do have two mutually exclusive outcomes, success and failure. Success in our case is considered rolling a 7, and failure is not. And then the probability is fixed for each of the trials. So we do have probabilities associated with rolling 2 dice that sum to 7. So that one, it seems, is indeed a binomial experiment. Let's look at a couple more. The largest 11 airlines had on-time percentage of 84.7% in November of 2001, according to the Air Travel Consumer Report. In order to assess reasons for delays, an official with the FAA randomly selects flights until she finds 10 that were not on time. The number of flights X that needed to be selected is then recorded. So we want to know if this is binomial. And I see one major problem with this right off the bat, and that's that this official is going to be selecting flights until she finds 10 that weren't on time. So we really have no idea how many flights need to be selected. So this one is actually not binomial because it's not a fixed number of trials. She might need to find 100 flights before she finds 10 that weren't on time. Maybe she needs 1,000 flights or 50 flights. It kind of depends. So it's not fixed. So that's why that one is not a binomial experiment. Okay, let's do one more. In a class of 30 students, 55% are female. The instructor randomly selects 4 students, and then the number of females is recorded. So we want to know if this is binomial. So it's good, it's a fixed number of trials because we have 4 students being selected, but I do see a problem here with this methodology. And that's the fact, if you imagine yourself sitting in this classroom, if you're one of the females who's selected, once you've been selected, you cannot be selected again. That wouldn't make any sense. So the trials are not actually independent in this case, because once you've been picked, you can't be picked again. So there are no longer 30 students left. Once you've been picked, there were only 29 and then 28, okay, and so on. So the trials for this one are actually not independent. Okay, objective 2 is to actually go ahead and compute probabilities of binomial experiments. So we have 3 main methods for doing this. We have a formula, which I'm going to walk you guys through. We have some tables in the textbook, which if you have a physical copy, I'm going to show you how to read that. And then you can also use, again, if you have a graphing calculator, the graphing calculator will do it for you as well. So I'm going to walk through the formula method first, and then as we do that, we're going to kind of talk about the table method as well. And if you want to know how to do it using your calculator, you can consult your textbook. Okay, so the probability of obtaining X successes in N independent trials is given by this formula here. So we have P of X, that's our probability, is equal to NCX. Now this you should be familiar with from chapter 5. Okay, this is a combination. And then we have P to the X power and 1 minus P to the N minus X power. And again, we talked about X, the values for X before. They're going to be somewhere between 0 and N. And then P, just like it was before, is just the probability of success. So this 1 minus P here is actually your probability of failure. So before we actually get into some of the problems, we want to talk about what various phrases correspond with which math symbols. So let's look at some phrases here. If you see the words at least, no less than, or greater than or equal to, then it's going to go with this greater than or equal to math symbol here. So these 3 things all mean the exact same thing. If you have words like more than or greater than, then that's just going to be your greater than symbol. If you have words like fewer than or less than, then that's going to be your less than symbol. If you have words like no more than or at most or less than or equal to, then that's going to go with your less than or equal to symbol. And finally, if you have words like exactly or equals or is, that's going to kind of signify that you should be using an equal sign, okay? And it's important to know the difference between these because it really changes how you do the problem. If you're doing a greater than problem, it's quite a bit different than doing a less than or an equal to problem. So it's really, really important that you know which of these words correspond with which of the symbols, okay? So we're going to kind of use this experiment several times when we're talking about some examples. So according to Experian Automotive, 35% of all car-owning households have 3 or more cars. Okay, so 35% of all households who own a car have at least 3 of them. So in a random sample of 20 car-owning households, so they walked around or whatever, and they took a nice random sample, which you've already learned about sampling. They took a nice random sample of 20 households that have a car, and they want to know what is the probability that exactly 5 of those 20 households have 3 or more cars, okay? So we know that 35% of the car-owning households have 3 or more cars. And we know that we sampled 20 people. We want to know what's the probability that exactly 5 have that. So the first way of doing this is using your formula. This is good to do a few times to make sure that you understand how the formula works, but I'm also going to show you guys how to get this value from a table. So if we have probability of 5, we know that we have n equals 20. So what we're doing is we're taking NCX, so 20C5, and then we take our probability of success. In this case, we would consider having 3 or more cars a success, and we raise that to the 5th power because that's how many cars we want to have, or how many people we want to have that number of cars. And then we multiply that by 1 minus 0.35 raised to the 15th power. That's your n minus your x. And if you do all of that in your calculator, you have to put it in pretty carefully, but if you do all of that, you end up with 0.1272, okay? And what that actually means is that you have about a 13% chance of getting exactly 5 households out of 20 who have 3 or more cars. So now, if you have your textbook, I'm going to give you guys a minute. You're going to turn all the way to the back where you have probably these tables that look a little bit crazy, okay? And I want you guys to turn to page A3. That's the first thing you're going to look at. And that's where your probability distributions are given for binomial, okay, which is exactly what we're doing. So again, that's page A3. If you're watching this video a little later, maybe pause it here until you find this page, okay? If you're accessing the online textbook, you can still access this. I'm not sure exactly how you type it in, but it's all the way in the appendix, okay? So you're gonna look at the appendix section, page A3 is where it starts. So what I wanna do is show you guys how to find this 0.1272 on a table, because it does exist on the table. What you're gonna see along the left-hand column is that you have different values for n. On page A3, it starts with n equals 2, 3, all through 7. Now, if we flip our page, you're going to see on the next page you have n is 8, 9, and 10. What we want is 20, so we need to skip a couple of pages, and what you'll see is that on page A6, that's where you have n equals 20. So what we're going to do is we're going to go down to n equals 20, and what we want is we want x equals 5, so that's our second column. So we need to go down to x equals 5. And then we have this whole row of numbers here. What we need to do is we need to find the probability that we have. And our probability is 35%, which is the same as 0.35. So you're going to kind of drag your finger over until you get into the column that has 0.35 up at the top. And I'll give you guys all a minute to do that if you're following along. If you go ahead and do that, so we're at n equals 20, x equals 5, and the probability at the top is 0.35. What you'll see there is the same value that we calculated using this kind of crazy looking formula. It's 0.1272, okay? So this table has all of the exact values up through n equals 20. It has, let's see, it has n is 2 through 10, and then it has 11, 12, 15, and 20. And then it has all of the kind of the typical probabilities. So it has probabilities that start at 0.01 and then go to 0.05 and then up by 5% all the way to 95%. So these are fairly typical. If you have a problem that doesn't have these values, like say you have n equals 25 or something like that, you are not, unfortunately, you're not going to be able to actually use this table. So this table only works for the values that it contains. If you have maybe a strange probability like 37%, then this table will not quite work. So at that point, you would have two other options. You can either use the equation that you have right here, or you can use your graphing calculator in order to compute that. Okay, we can also ask other types of questions. So this is the same setup. We still know that 35% of all car-owning households have 3 or more cars, but this time we have a bit of a different question. It says, in a random sample of 20 car-owning households, what's the probability that less than 4 have 3 or more cars? So the difference between this one and the last one is that we have less than. The last one we had exactly 5. This one we have less than 4. So you always have to kind of think back to, let me move back here, this page right here, and figure out what math symbol we're going to use. Now, less than, that's an easy one, okay? So what we have right here is we want the probability that x is less than 4. So that's this right here. Now, we don't want x to equal 4. We want x to be less than 4. So anytime you're doing these types of problems, you always want to rewrite your inequality so that you have less than or equal to, okay? So if we're talking about a binomial experiment, you're talking about discrete values, okay? We're not talking about, we can't have 3.5 households that have 3 or more cars. We either have 0, 1, 2, 3, 4, and so on. So you can rewrite this probability of x is less than 4. That's equivalent to saying probability that x is less than or equal to 3. Okay. So the probability that x is less than 4 is actually the same thing as saying that the probability that x is less than or equal to 3. So if you look at this, if you're thinking about the actual problem we have on hand, we have a random sample of 20 households. That means if we want x less than or equal to 3, it means that we could have 0 households that have 3 or more cars. We could have 1, 2, or 3, okay? So one option that we have is to compute all of these probabilities using the formula that was like this one back here. So we would calculate that 1, 2, 3, 4 times, and then we'd add everything up and we would get this number. Now, as you may guess, there are nicer ways to do this. So if you still have your book open to that appendix that we were looking at, we were looking on page A6. And if you notice, if you go back, keep your place where you are, but if you go back to A3, it has a note there on the top. This table computes the probabilities of obtaining X successes in N trials, and it gives you the probability P. Now, if you look on page A7 instead, this one has a slightly different title and note. It says cumulative binomial probability distribution. So this table computes the cumulative probability, okay? So this one accumulates your less than or equal to. So anytime you have a less than or equal to question, you can use this cumulative table. So again, we're gonna flip to where we have n equals 20, except we're going to be on our cumulative table now. So that's all the way on page A10. So if we go over to n equals 20 and x equals, let's see, what do we want? We want x less than or equal to 3. So we're going to go over to 3, or down to 3 rather. And then we still have that 0.35 as our probability. So we're on n equals 20, x is 3, and then we kind of scroll our finger over until we get to 0.35. And what you should see is the same value that we have on our screen right now, which is 0.0444, okay? So those two values match. So one way of doing it is to use your formula and calculate those 4 different values and then add them up. The other option is to just look it up on this table, which is pretty nice. All right, the last type of question that you have with this is something where you have greater than, okay? So this one says, in a random sample of 20 car-owning households, what is the probability that at least 4 have 3 or more cars? So if you think about at least 4, that would mean we'd have 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way up to 20, okay? So that's what we want to have happen. Unfortunately, we do not have a nice table for when we have greater than. So what we need to do is we need to change it to a less than or equal to problem. So if you think about this, and sometimes the easiest way to do this is to draw yourself a number line, okay? On your number line, you would have values of 0 to 20. So those would be all of your x possibilities. What we want is the probability that x is greater than or equal to 4. And if you think about all of the probabilities, when we add them all up, it has to equal 1. So the opposite that we go on to kind of think about is what is equivalent to saying that, but with less than. So essentially what we can do is we can do 1 minus the probability that x is less than or equal to 3. And we already looked up that value. Probability that x is less than or equal to 3 is just 0.0444. That's the value we just looked up on our table. So you just have to do 1 minus that value. So what I kind of want to point out here is that we have 3 different types of problems with probability distributions for binomials. So if you have a question where it asks you for exactly that amount, all you have to do is look on your binomial exact table, and that will be your answer. If you have less than or equal to, all you have to do is just look on your cumulative table, and that's going to be your answer. But if you have greater than or equal to, then you need to change it into a less than or equal to problem and then do 1 minus that value from your table. So there are kind of 3 options there. Objective 3 in this section is to go ahead and compute the mean and the standard deviation of a binomial random variable. So we have a mean, or we can call it expected value, and a standard deviation formula for binomial random variables. And these are actually, I hate to say easy, but they're pretty easy formulas. They're a little easier than the other ones we've seen in this section. So we know that there are n independent trials. We know that the probability of success is p, and we know that the standard deviation is going to be denoted with this symbol right here. So in order to find mu of x, that's your mean, all you have to do is take the number of trials and multiply it by the probability. The probability should be written as a decimal, not a percentage. And then in order to find the standard deviation, all you have to do is n times p times 1 minus p, and then take the square root of that, and that will give you your standard deviation. So let's look at the same example, except this time we're taking a random sample of 400 cars. 400 car-owning households. So we have 35% of all car-owning households have 3 or more cars. We're taking a simple random sample of 400 households, and we want to determine the mean and the standard deviation, okay? So in order to find the mean, all we have to do is use that nice little formula. We have mu of x is equal to n times p. If you remember, n is the number of trials, which in our case is 400, and p is the probability of success, which in our case is 0.35. So all you have to do is just multiply those two numbers, and you get 140, so that's your mean. Standard deviation, all we have to do is take square root of n times p times 1 minus p. So n is 400 again, p is 0.35, so we just plug all of that in. If you have trouble using a calculator, my suggestion is go ahead and do whatever's under the square root first, and then take the square root, and you should get 9.54 for the standard deviation. We can also construct binomial probability histograms. Now, we already talked about what a probability histogram is, so we're going to look at a couple of examples, and this is going to illustrate kind of an important concept for us. So we're going to start with this one where it's we only have 8 trials, so we have n equals 8, and we have a probability of 0.15. And if you notice this, we talked, I think, about skew in a previous chapter. This one is definitely skewed to the right. It has kind of a tail that's going to the right, okay? We always talk about skew in terms of where the tail is. So this one is skewed to the right. If we look at this one right here, we have n equals 8 and p equals 0.5. This one is pretty good. This is pretty symmetric. It's bell-shaped. Looks pretty normal. Okay, so this is a good one. And then if we look at n equals 8 and p equals 0.85, this one's definitely skewed to the left. You have a tail kind of hanging out here on the left. All right, so this one's also a little skewed. The next thing we're going to look at as some binomial probability histograms with different number of trials, okay? So we're going to start with n equals 25 trials and p equals 0.8. So if we do this, what we see is there's definitely a little bit of skew here, okay? And then I'm going to click through these. We have n equals 50 next. And you might notice what's happening. Let's look at one more. We have n equals 70. What you should notice is that as we have a larger number of trials, so as n is increasing, what you should see is that our distribution starts to look more and more normal. So we have kind of a nice little rule that kind of states this. So for a fixed probability of success p, as the number of trials n in the binomial experiment increases, the probability distribution of the random variable becomes bell-shaped. And then we have this kind of general rule of thumb. So if n times p times 1 minus p, so if you multiply those 3 things together and you get at least 10, then what we would say is that our distribution is approximately bell-shaped. And if this is true, then we can use something called our empirical rule, which I think you guys learned in a previous section, in order to identify unusual observations. Excuse me. So the empirical rule states that in a bell-shaped distribution, about 95% of the observations are within 2 standard deviations of the mean. So if we think about this for a minute, 95% of our observations are going to be between mu minus 2 times our standard deviation and mu plus 2 times our standard deviation. Any observation that is outside of that interval or outside of that range can kind of be considered unusual because it tends to happen less than 5% of the time. So let's do one example with this. According to Experian Automotive, we have the same kind of thing happening. 35% of all car-owning households have 3 or more cars. A researcher believes this percentage is higher than the percentage reported by Experian Automotive. And he conducts a simple random sample of 400 car-owning households, and he found that 162 of them had 3 or more cars. So we want to know if it's unusual. So what we need to do is we need to calculate our mean, okay? And we actually already did that. We took n times p, we did this before. N is the number of trials, 400. P is your probability of success, which is 0.35. So we got a mean of 140. Standard deviation, this is the same calculation that we did before. And when we calculated, we got 9.54. So what we need to do now is we need to figure out what is our lower bound. So we need to take our mean and subtract 2 times our standard deviation. So we take our 140, that's our mean, and we subtract 2 times our 9.54, and then we do the same thing with addition. So we take our mean plus 2 times our standard deviation, and what we end up with is this kind of interval from 120.9 to 159.1. And what we would say is that the result that they got from that experiment that they did is indeed unusual because 162 is actually larger than 159.1. So that would be considered an unusual observation. So that's actually it for the Chapter 6 stuff. I'm not sure. I think I had an attendee, but I don't see them online, so I don't think there are any questions. Yeah, I just checked. It doesn't look like there are any questions, so we'll go ahead and end the webinar there. Thanks for joining in, and we'll see you next week.